Okay, so in B it says calculate the number of times P returns to its initial position B in 10 seconds. Well, if you think about it, it starts at B, doesn't it? It's held at B, and then it's released. And of course, because there's so much tension in that spring, it speeds back to its natural position, but it's going so fast, then it continues and goes to the other extreme point. And we've got SHM, and it returns back to B. Now that takes pi over 3 seconds, yeah, because we worked that out before in part A. That's the time period. So it takes pi over 3 seconds to get from the start, okay, to complete then its journey back. Okay, now I worked out on the calculator to be about 1.047 seconds. Okay, so then how many times can it do that? Basically in 10 seconds. So you just got to see how many of these would fit into 10 seconds, essentially, yeah? And if I do that, okay, I'll have 10 seconds then divide by, well, instead of using that, I'll just use pi over 3. And if you do that on your calculator, it comes out to be 9.549, okay? So in other words, it will complete 9.549 of these. So 9.5, roughly, yeah? So after it returns the 9th time, it will then go on its next journey and it'll get to about halfway or just a little bit more than halfway, and then the 10 seconds will be up. So it hasn't quite got time to get back to B again. So in total, it will return 9 times. Okay, 9 times to B in the 10 seconds. So it's going quite fast, obviously, right? So in C then it says find the greatest speed of P during the motion. Now we know greatest speed occurs when it gets to the mean position, yeah? So greatest or max speed occurs at O, okay, the mean position. And we know that Vmax is equal to omega A, right? We can see that from the formulas. Now we know that omega is 6, and we know that A is 0.5. We've worked all that out, right, in part A. So the max speed turns out to be 3 meters per second. So you can look back at that if unsure. Then it says in the next bit then, what does it say? So it says the point C is on the path of P such that AC is 0.9 meters. So let's see where this would roughly be here. So if you think about it, the amplitude is 0.5 meters, isn't it? Okay. So 0.5 meters there, but it says AC is 0.9 meters. So 0.9 meters would be about there, isn't it? Roughly. So C is going to be there. That's going to be 0.9 meters. And more importantly, that means that this distance here, if you think about it, will be 0.3 meters. Okay. And that is really important, I think, for the next bit. So because this is 0.9 meters here, that's got to be 0.3, isn't it? Because the whole thing is 1.2. So it says then, in D, find the time taken for P to reach C for the first time. For the first time, think about where it starts. P starts here, doesn't it? It's held here, then it goes from here through O all the way to C. So we need to work out the time it gets from B to O to C. Now I can work out O to C really easy because I can use the formula I've got, x equals A sine omega t. B to O, okay, well there's actually two ways you could do it, right? You could work out O to B and use the A sine omega t formula, okay, or you could work it out from B to O, and because it starts at the extreme, you've got to use the A cos omega t formula. Or another way, think common sense about it, to get from B to O, if you think about it, that's actually a quarter of the oscillation, if you think about it logically, because to get from B to O, okay, is like is a quarter if you think of the whole oscillation, because that's like the amplitude. You've got the amplitude again, you've got the amplitude again, you're back to B. So that journey from B to O is like 1/4 of the journey, isn't it? Okay, so you could say, look, from B to O is quite simply 1/4 of the time period. All right, does that make sense there? Now we know the time period was pi over 3, okay? We worked it out in part A. And that works out then to be pi over 12 seconds. So we've got B to O, now we just need to work out O to C. So O to C, okay, well if you think about it, it's that displacement there of 0.3 meters, so x will equal to 0.3 meters. And if we use then, because it goes from O, if you use x equals a sine omega t, okay, well, we know x is 0.3, we know a is 0.5, because we worked all this stuff out before, yeah. We know omega is 6, and we've got that there, yeah. So then we just do a little bit of movement around here. So 0.3 divided by 0.5 is equal to sine 6t, okay. Take the sine over, so sine to the minus 1 of 0.3 divided by 0.5 is equal to 6t. And then take the 6 over, so it'll be 1/6 of that. Equals t, okay? So then that implies then, that comes out to be, check on your calculator, 0.107, so the total time will be 0.107 plus the pi over 12 for the journey from B to O, so we worked out that, and that comes to 0.369 seconds. Okay, and it says then to work out the speed at C, yeah, for the very last bit. So the speed at C, so at C then, the speed, well, if we use v squared is omega squared a squared minus x squared, okay, so we've got v squared 6 squared, a is 0.5, x will be 0.3, yeah, okay, and if you work all that on your calculator, you get v then out to be 2.4 meters per second, okay.